Hello, everyone. My name is Jacob Elkins. I'm a graduate student researcher at the University of Alabama. And before I get started, I would just like to thank you and say I really appreciate you coming and watching my presentation on my recent research. So I'll be talking today about adaptive continuous control of spacecraft using reinforcement learning. This is done under Dr. Rohan Sood at the Astrodynamics and Space Research Laboratory at the University of Alabama in coordination with Dr. Clemens Rumpf, who is an aerospace engineer at Science and Technology Corporation based out of NASA Ames Research Center out in California. So I'll go ahead and get started. So a little overview about what we will be talking about today. I'll go over why we did it, so the motivation behind the study, the basics of reinforcement learning to get you up to speed on what we'll be discussing today, how we simulated the spacecraft attitude control problem so that reinforcement learning can understand it and work with it, the specifics about our reinforcement learning implementation and what drives our success for the agent, the state and reward formulation, which is of the utmost importance to a successful RL implementation, some control examples, and then specifically kind of the highlight of the study is that some disturbance torque examples, so showing the adaptive nature of our agent. So motivation. So why did we study this? So autonomy, it's really well defined that autonomy is going to be essential in our space capabilities going forward. The space environment is a very harsh environment. Physically, humans can't go there, so we need to send robotics and autonomous spacecraft to increase our capabilities. You think of modern spacecraft constellations, even in low Earth orbit, and that's good. That seems to be the future. And modern machine learning technology really shows a lot of promise there. Specifically, reinforcement learning. It's a highly active research area of machine learning, and studying how you frame a problem for the machine to understand, I think, is of merit going forward. As the field of reinforcement learning progresses, these capabilities need to be brought to the space industry, and I think this is going to happen in two ways. I think modern machine learning is going to extend human capabilities, so allow us to do things that we weren't able to do beforehand, and then improve current approaches, so allow us to do the things that we've already been able to do in better ways. So reinforcement learning, it's actually not specific to machines. It's a generalized nature-inspired learning framework. So our agent here, that's a common terminology of reinforcement learning. An agent here, it could be, let's say, a dog or a human, or in our case, a spacecraft. And the agent sends an action and interacts with the environment to receive a reward signal. My favorite example of this is, let's say you teach a dog how to sit. You tell the dog sit, he sits, you give him a treat, and the dog, it's reinforced for the dog to take the action sit in the environment of you saying sit, and receive the reward, the treat. And in humans, this reward would be like a dopamine signal. This is how our brains are kind of reinforced to learn and perform certain actions with dopamine as the reward. So really interesting. And it's usually framed mathematically as a Markov decision process, an MDP. It has a sister in the partially observable case called a POMDP, a partially observable Markov decision process. And inherent to the MDPs are discrete time episodes. And so, of course, our real world is a continuous time, continuous space, state space, and often continuous action space. So a lot of care needs to be taken in discretizing these continuous time and continuous state space problems into these discrete time episodes that are inherent to the MDP that RL is based off of. So how do we simulate the spacecraft attitude control problem mathematically? So starting at the top left here, you'll see the familiar Euler's rotation equation, and we integrate this equation using run-coda order 4 to find the value of the body fixed angular velocity of the spacecraft at the next time step, given an input from the agent m. This m vector is a moment vector or a torque vector that's actually input from the agent. And then we define the spacecraft attitude and represent it as this error quaternion, Q sub e, which is defined as this e hat. This is all diagrammed here on the right as well. The e hat is the axis of rotation, and then the angle phi is the angle of rotation about that axis, e hat. And then we integrate this equation, Q sub e dot, for the rate of change of the error quaternion using this, again, run-coda order 4, and this capital omega matrix is the skew symmetric product matrix of the body fixed angular velocity. And here's the relationship. We want to teach the spacecraft to perform a large angle slew from this body fixed frame to the desired frame sub DES here. So to study how comparable our agent was to real world industry standard pointing accuracies, and to study the interaction between our agent that's trained in a simulator and then that transferred to the system to a real world system, we decided to model the Lockheed Martin 50 nanosat system, which is a 4 to 6 volume, 4 to 6 U volume nanosat, which Lockheed Martin denotes that the total pointing accuracy of the LM50 is less than 0.25 degrees per axis at the 3 sigma level. And this allows us to directly compare our agent's pointing accuracies to what is industry standard. You can see the LM50 system that we modeled rendered here in Blender on the right with the body fixed principal axes labeled. So here we go over some specifics to our reinforcement learning implementation. There are numerous algorithms that aim to solve the Markov decision process I mentioned earlier. So we decided to go with an off-policy, state-of-the-art continuous control algorithm called Twin Delayed Deep Deterministic Policy Gradient, or TD3, from Scott Fujimoto in 2018. We opted with TD3 because it shows a little bit more promise in its ability to explore than some current on-policy state-of-the-art methods such as proximal policy optimization. And here I have a diagram of kind of the generalized off-policy framework. So starting here in the red box, the learner box, here we want to optimize our policy and our state action functions. So we're actually approximating two functions that I'll mention in a second. So we take this current learner, so the current network parameters, using a neural network as a function approximator, and we send it to the environment to interact with the environment and explore based on our exploration policy. And for TD3, the exploration policy is you sample an action from your policy, and then you add a Gaussian noise vector with a mean of 0 and a standard deviation such as 0.1 or 0.2. And then you send all these experience tuples, this state, action, reward, and then the next state values into a centralized replay buffer where you store the experience that the learner then samples many batches out of to optimize its policy and state action functions. And this happens iteratively. So you go around this diagram. So reinforcement learning makes use of deep neural networks. It's critical. Basically, the learning that goes on is you're approximating functions. And the two functions that you're approximating are the policy and the cue function. These commonly take the words actor and critic. You'll hear that's a family of algorithms called the actor-critic algorithms. And the policy here is denoted as pi, which your outputs an action given a state. So it's the mapping of states to actions. And then your cue function is your state action value function, how it's called. So it's the cue for a certain policy pi is denoted here. It is the expected value of this capital R, and that's the returns. So the expected value of the future returns for a state given an action. And capital R returns for a certain state is denoted as the sum of the discounted future rewards to some time step t, capital T. And then that gamma is a hyperparameter. It's your discount factor, which is usually on the order of like 0.99 or above. We stick with 0.99 here. And then I diagrammed here on the right, I show just a simple diagram of a fully connected neural network with two hidden layers. So that's commonly called a multi-layer perceptron. And we use these because we need, deep neural networks are very powerful nonlinear function approximators, and we need some high fidelity function approximation to find this policy and this cue function. So driving the success of your reinforcement learning implementation is, in my opinion, two things: your state vector and your reward. These kind of show that it's essentially how you represent the problem to the computer. And so for our state vector here, and this is a big motivation of our study, is to figure out how we should represent and how we should reward the agent for our spacecraft attitude controller. Our state vector is that error quaternion that we mentioned again, the rate of change of the error quaternion, and then your body fixed angular velocity values. So the reason that we went with this was the error quaternion is a generalized and totally relative representation of your attitude. It doesn't take into account any, let's say, arbitrary coordinate frame, such as an inertial frame. And then to preserve that Markov decision, that Markovian memoryless property, you need to have the rate of change. So this kind of tells you where you're at and where you're going. And then the body fixed angular velocity is included because that's what the agent can directly control via the torque vector. And then the reward kind of changes during our episode to reflect the evolving goals. So our problem's kind of split into two goals. So first you want to navigate to a goal orientation. And to do that, we have this R sub T, your reward. It's really simple. We try to avoid a lot of the problems that you face with reward engineering with this either 0.1 or negative 0.1. So you get a 0.1 reward if essentially your scalar part of your quaternion at this time step is better than the previous time step. So that reflects that you have a smaller angular error, and then otherwise you get a negative 0.1. So this incentivizes the agent to navigate and get closer and closer at each time step to the goal. And then if your goal is reached, so again the goal is defined for the LM50 satellite as an angular error of less than or equal to 0.25 degrees. We switch to this reward function. So we define this alpha vector, which is kind of gives us a little bit more fidelity in that quaternion, since at this angular error, the quaternion values get close to 0, 0, 0, and 1. So this gives us a continuous reward function that's on the order of about 1, that says how close and how small is that angular error. So this incentivizes to not only get to the reward, but also stabilize about that goal orientation, if that makes sense. So here I'll go through some control examples and visualize what the agent is actually doing in the environment. And this one was with no disturbances. So the first test that I picked was performing a 100-degree slew about the axis that is equal parts in the first octant. And here we have a real-time GIF render of the spacecraft on the left with the orientation in real time as well on the right. And the control fidelity of the agent here is about 11.4 hertz, and the way that is implemented is the time step integration fidelity is 1/240th of a second. I picked that to be consistent with industry standard simulation environments such as PyBullet and the popular Bullet physics engine. And the agent selects an agent at one time step. That torque vector that the agent selected is propagated in the subsequent time step, and then the next 20 time steps are integrated with free rotation, so zero torque. So that gets a control hertz of about 11.4 hertz. And so the first disturbance example was a detumble scenario, and we picked this to be kind of like a deployment or a small sat coming out of a safe mode, and where it's acquired some angular momentum in the time that it was in the safe mode with zero control. And the initial condition and the way that this is implemented is an initial body fixed angular velocity of 1 radians per second, 2 radians per second, and 5.5 radians per second. And we picked this value to be consistent with Farhad Aghili in 2004, who published a paper on time optimal detumbling of spacecraft from the Canadian Space Agency. He predicted a full passivization of the spacecraft's angular momentum at 19.34 seconds into the simulation. And our rotational inertia tensor is a little different than their test, but we achieve about 0.05% passivization at 19.5 seconds into the simulation. So it suggests that we have a really close approximation of time optimality in our spacecraft controller, which is very interesting. So I'll let that play one more time. You see the spacecraft slews to the desired orientation and stabilizes at about 19.5 seconds. It's cool. So the second disturbance example that we decided to model was a single impulsive torque, and we decided this torque magnitude to be 5 newton meters, 2 newton meters, and 1 newton meter at t equals 15 seconds into the simulation. And we picked this value to kind of replicate something like a faulty thruster, which is implying it or imparting a torque vector onto the spacecraft, and then you quickly shut it off. And so we applied the disturbance at t equals 15 seconds, so right there, that bump, and then the agent this is unseen during training, and then the agent is able to slew back to the desired orientation, which is very interesting. So the third disturbance example that we modeled was a constant disturbance torque, and we modeled this such as something like gravity gradient torque that the spacecraft could experience. And we decided to pick the upper limit, essentially, of what the spacecraft could encounter. And so we went and found what the gravity gradient torque that the spacecraft Juno encountered around Jupiter at perigove. And so it actually is about the order of magnitude of 0.05 newton meters. And then I wanted that dependence on rotational inertia as well. And so this torque that's described there is imparted on the spacecraft at each simulation time step. This is again unseen during training, and the agent is still able to perform effectively with the presence of that disturbance torque that it did not see in training. So very adaptive and interesting. So I'll let it play out. Very cool. So the fourth and final disturbance example that we decided to model is changing the rotational inertia tensor over the lifetime of a spacecraft. Let's say you deploy deputy spacecrafts, and so your mass and your inertia change, or you deplete your fuel tanks. And so to describe this, we picked the rotational inertia tensor to just be half component-wise what the original inertia tensor was. So the spacecraft, you can kind of think of this as, it's almost like the spacecraft has a little bit more control authority over the spacecraft since the rotational inertia is depleted. And again, this is unseen during training, so the agent is able to generalize and adapt to a different inertia tensor. So very interesting as well. So I'll let that play out. So finally, we conclude that RL is a feasible method for deriving a spacecraft attitude controller. The derived policy is not only adaptive but system agnostic. We showed that the policy can perform with different rotational inertia tensors, and it's resilient to conditions unseen during training, which is crucial because you can't possibly model every disturbance torque that the agent will see in its lifetime. And I think some avenues of future work would be a master policy, so one really good controller neural network that can control multiple spacecraft, and you refine it to specific mission needs. I think of this as like a ResNet 50, which is a popular computer vision neural network, where let's say you freeze the previous layers of the network, and then the last one is trained to refine the specific mission needs. So I really appreciate y'all coming to our presentation and following our research. If you have questions, please join the Artificial Intelligence and its Applications to Space Missions virtual room on August 12, 2020 at 11:50 a.m. to noon Eastern Daylight Time. Thanks again. My name is Jake. I really appreciate y'all listening to my presentation, and I hope y'all have a great conference.